We're going to look at hypothesis tests and confidence intervals, but for means this time. So we conducted hypothesis tests and confidence intervals for the proportions, and now we're going to do the same thing, but for means. And the good news is that all the theory, everything you worked so hard, still applies here. Okay. The formulas used will contain the same construct, but there are some differences in the distribution we're about to work with. So what is the same? So the central limit theorem is still in effect. We need the sampling distribution of the mean to be approximately distributed. Okay, so and we achieved that. So that requires that my sample size be large enough. Right? Or the population of our data comes from a normal or symmetric. Or it's a lot of ors. If skewed, very slight, with no outliers or no extreme values. Okay. And again, what I mean by this is that, if it's a small sample size, then we definitely wouldn't need to be normal or nearly symmetric, or if skewed, very slight, if again, my sample size is small. Okay. We definitely require that the sampling process be unbiased. That is always going to be, no matter what, the requirement for anything. So what is different here? Well, when introducing sampling distribution of the mean, the population mean, and the population standard deviations were given. Okay, so remember when we were doing this before, those components were part of the given. So for hypothesis test, the mean is assumed to be known, and the standard deviation, and these, again, what I mean by the mean assumed to be known is population mean. And for the standard deviation, we will use the sample standard deviation from the data. And my light in this room just went off, so maybe we'll stay down for a second. Yeah. So for confidence intervals, neither is known. So for both the mean and, let me call it standard deviation here, will come from data. Okay, because again, the standard deviation is not known. We no longer can use the C distribution. Instead, we will use something similar called its full title is students T distribution. Okay. And we're going to definitely talk more about this distribution. So one thing also to know, the smaller the sample size, the more we need the data set to be more symmetric with no extreme values. As the sample size increases, we can relax some of these rules. So that's something that we saw with the central limit theorem before. Okay, so let's look at students' t distribution. This distribution is definitely bell-shaped. So that part hasn't changed, just like the normal. But its overall shape depends on the sample size of the data. So there's not one. It is wider at the end than normal distribution, and as the sample size increases, the t distribution approaches a normal distribution. Okay, so that's something different here. So there's not going to be a one curve for the t distribution. It is based on sample size. The shape, though, it is just it looks like a normal bell-shaped curve. Okay, but what's the difference then? It's going to be definitely wider at the ends. That it's is thing. And why is that the case? Because we're going to have to use the sample standard deviation in our calculations. So remember, sample standard deviation is S. And when we do that consistently, you'll see that the data produces a larger value for S. And remember, sample standard deviation is nothing more than an estimate for sigma, population standard deviation. So when S tries to estimate sigma from a sample, S will always be, I mean, pretty much you can bet money on it, bigger than this. So we need to make adjustments to the normal distribution, and that's what students' t distribution is. Okay, so there's a particular distribution depending on the sample size. Okay, so we talked about that. We use this concept called the degrees of freedom, abbreviated. Sometimes you'll see DF or D period F or whatever, but you see DF and it's degrees of freedom. Okay, and what are the degrees of freedom? Okay, well, let's find out. Degrees of freedom, DF, is just going to be n minus 1. That's all that it is. Now, you're wondering, what is the degrees of freedom? It sounds very patriotic, but it has nothing to do with patriotism. So here's a way to look at this. Let's say I'm going to add 3 numbers, and I need them to add up to 12. Notice you have here 2 degrees of freedom. Why? Because let's say that I randomly choose 3. Then I randomly choose 7. So the first 2 numbers, you can be whatever you like them to be. You have 2 degrees of freedom. But once you choose the first 2, the third is no longer an option. It has to be a 2, right? That's what it's got to go in that slot in order to get the 12. So that's what degrees of freedom mean. How many things can we actually choose? And then there's always going to be 1 or 2 or 3 or however many that you do not have that freedom. Okay, that's what degrees of freedom are. In GeoGebra, we use a drop-down menu selection to choose students' t distribution, which is just, you'll see it as called student, to find probabilities or critical values. The students' t distribution was created by William Gossett for the purpose of quality control in the beer production for Guinness Brewery in the 1900s. Gossett noticed that for small sample sizes, the normal distribution did not provide good results. And by using data, comma, and this data, comma, I guess, discovered an issue in calculations when population standard deviation is not known. Okay, so Gossett could not use population because he didn't know it. It was quality control. So it was using just the sample standard deviation and started running into a problem. Before that, there was, I mean, other people would use S, but the sample sizes were large, very large, large enough that this wasn't a problem using this value. Okay, but when it's small, all of a sudden it becomes a problem. Okay. Now, why is it called students T? Because when when William Gossett discovered this, there was a policy at the Guinness Brewing Company that he could not publish because of proprietary reasons. So instead, William Gossett published under the pseudonym student. So that's how he got the information to the world. And so for that point, it's always been known as students T distribution. And what is let's say I'm looking at single mean T statistic. What is the formula for my single T statistic? Well, it looks like this. So notice it's going to be pretty much as it was before for sample means. What's the big difference? It's that we're going to use sample standard deviation. Remember before, this formula looks something like this. So we'll use population standard deviation. So here we admit we just don't know what this value is. And when we do hypothesis, notice again that this is something that is assumed to be known. How that comes about varies from situation to situation. Okay. So let's look at a particular scenario here. A particular type of apple tree yields apples that on average weigh 150 grams. A farmer is using a new type of fertilizer to see if the average weight of the apples can increase from the current amount. We will construct a hypothesis test, set the significance level to 5%. So what do I have here? A particular type of apple tree yields on average 150 grams. So again, the way this is stated, let's assume that this is known and correct. So what I have is this. Mu is 150 grams. Okay, so that's for my population. So this is the population. What's going to be the alternative? Well, still going to use, again, notice I'm using a parameter, mu. And what is it I want to know? Well, I want to see if the average weight of the apples can increase. Okay, so increased. So it looks like we're heading in a particular direction greater than. So we're going to do this. So 150 grams, 150 grams. That's what we're after. Okay. So a sample of 14 apples coming from this tree yield the following weights in grams. And here we are. Okay. So you download a file that is in the content, and I'm going to open it up here in GeoGebra. So again, I'm going to go to my pancake thing here in GeoGebra, and I'm going to go to view. Oh, it's called the hamburger. That's what it's called. Click select spreadsheet, and I'm going to get rid of algebra and graphics because I do not need those, and I have that information. Great. And I also created a file. Again, you can download and up this information. So let's do that right now. I'm going to go to file. Again, back to the hamburger, hit file, open, and it's going to be a local file. So I'm going to click on here. And I save mine under downloads. So I find it, open it up, and there's my data. And again, looks like all this stuff here came. I'm going to get rid of it, go back to the hamburger view and get rid of algebra and graphics. I guess it got copied over from last time. Great. All right, so what I'm going to do is here's the data that's sitting right here. I'm going to highlight this. I'm going to click back to histogram again. Yep, got to click a couple times. One variable, there it is. For some reason, I got to click a couple times. And you can see what the graph looks like. You know, what kind of shape is this? It's definitely looking, I don't know. Certainly doesn't look that symmetric, does it? So let's come over here before we continue and do a normal quantile plot. And look at that. So I'm going to come over here. So create a QQ plot or normal probability plot. And again, here's called normal quantile plot. Again, many names. But on GeoGebra, it's called a normal quantile plot. And just draw yourself a little picture of this. Just rough. So what I got, again, is a very rough picture. Just to give me an idea what's happening. And again, notice the middle part here is great and looks like also going to get these 4 values and this one. So what's happening with these 4 values? I'm sure there's a lot of repeat or very close to repeat. These are not in order. So there's some like 110, 110. It's the 110. I'm looking over here. Yep, it's the, here we go. So I'm looking at 110. So yeah, there's a lot of repeats in the 110 area. And that's causing this little spiking. There's 109. So yeah, that's all that's happening. So it's got bunched up there. But does this say that it is sort of normal? Because yeah, again, except for this weirdness here, but that can happen. You know, fairly straight. And again, what I'm looking for also is that out, you know, the one that's sitting all by itself. It's not that far from that line. So I'm going to say this is good. Okay, so data seems to come from a population that's, you know, approximately normal distributed. Yeah, so not bad. And again, so I'm grabbing 14 values, even if it was a little bit off, the 14 should be large enough to offset any skewness that might appear. So, okay, I'm happy with that. But now, of course, I'm going to need to use the sample mean standard deviation. You're not expected to do this by hand. That's why I'm copying this information here. I'm going to click on this sum, and then the information pops out. In the homework, again, you'll have data, and you can copy and paste it on down here. If the online version, like I'm using here, is giving you trouble, then maybe go down to the downloaded version of GeoGebra. Or there might be another device where you can just copy and paste the data and you can just get this information. So the sample mean here is right there, 105.095 grams. And the standard deviation, again, notice it gives you 2, but you need to use a sample standard deviation. And you might be wondering, well, isn't that what we want? The sigma? Didn't just calculate sigma? And the answer is no. This would be sigma if what I've just entered is the entire population. So there's 2 formulas for standard deviation. One if you're actually entering the entire population. One if you're only entering a sample. And we only entered a sample. So I got to use this one right here, 7.644 grams. All right, fantastic. So now we got that information. I'm also going to use Desmos to enter numbers in here. And again, the light that the room I'm in, the light keeps turning off. It's on a timer. All right. So now I'm ready to do my t-test statistics. So it looks exactly like I did before. I mean, here's a formula. There's nothing really special about the way I'm doing this. So I enter my mean. minus the mean of the null divided by my standard deviation, square root of, and then I got 14 values here. So I do all that, and notice I'm going to just enter this as one shot here into, I'm using Desmos, it's a free online calculator, and I'm going to put parentheses to signal I am looking at the numerator, subtract the null, then I'm going to hit the divide key. I'm usually with the key here in my keyboard, or you can use the divide key here button. Then I'm going to enter 7.644, and again I will hit the divide button. I'll do that here just so you can see it, and it creates this. And I'm going to square root. I can click the square root button and type 14, and I see that my result is negative 21.98. So okay, so this is pretty extreme, right? I mean, well, I'm going to go a little more. It's fine, but this is so extreme that I just don't care anymore. I stopped caring. So let's think about this for a second. 150 grams is the current yield. I'm looking to see if there's evidence that is bigger than 150. And not only did I not do that, but my sample mean is 105, which happens to be 21.98 standard deviations to the left of where I'm not. So this is obviously something's wrong with it. I mean, do we need to do it just a calculation here? The answer, of course, is no, because that there's nothing here. We didn't find any evidence. Okay, but I'm going to go through the process anyway, and I'm going to draw a picture just to make sure we are all on the same page. And it's easy to get confused at this point because everything is not where I wanted it to be. So it's 150. I got 105.095. Okay. Now I looked at my direction. This tells me go to the right. So if I landed to the left, if I'm going to calculate the p-value, it's going now to the right because of my alternative. My alternative says greater than 150, so I have to go in this direction. So this area right here is my p-value. So what I'm going to calculate is what's the probability that, again, my sample average is greater than 105.095, which as a t value is negative 21.9805. And now I'm going to calculate the p-value because this is the p-value right here, this whole area. Now, I mean, the answer is just going to be 1 or nearly 1, right? 0.9999999 and so on. So just about 1. But let's go through this so you can see how this is done. All right. Let me move down a little bit. I'm going to go to GeoGebra. Right. And I need to use the probability calculator. So click on that. And the probability calculator moves across. All right. There we have it. Probability calculator, happy. Now, the default, of course, is normal. But I don't want normal. I want student. So I'm going to choose student. And you'll notice something. Now, mu and sigma are gone. Notice before you can actually change things. Now you cannot. So this is one situation now. From now on, except for normal, all software does not give you the opportunity to change the mean or standard deviation. You must standardize. And we're standardizing it by calculating a t distribution. What you must change is the degrees of freedom. So in this case, what are my degrees of freedom? Well, my sample size is definitely 14. So I need to subtract from 1. So the degrees of freedom is 13. So I got 13 degrees of freedom. Oops, not 113, 13. And notice how the shape changed. You see how the shape, let me just put one more zero. Notice how the shape is changing. Look at that. If I have 1 degree of freedom, a sample size of 2, look at that curve. Anyway, that's not it. It's this. It's 13 degrees of freedom. I'm going to go to the right. I entered. I'm just going to make it 21. Negative 21, of course, it just says that it's 1 because to 4 decimal places, it's 0.99999. So another thing to notice how the standard deviation is bigger for the t distribution, because again, it's trying to allow for the variation that you would see from sample data. All right, so what's the interpretation? We did not find any evidence that the use of fertilizer will increase the yield to some value greater than 150 grams. Okay, so that's really what we have. So we failed to reject the null hypothesis. All right. As a matter of fact, it seems like we found the exact opposite. The yield is going down using this fertilizer. So the exact opposite we wanted to show. Let's look now at this other part. So we're going to stop the video and come back to it.